So use geometry and the properties of definite integrals to evaluate them. So we're going to go through the list of definite integrals. And this is something you probably want to write down or reference in the book. Integral from a to a of f of x dx is 0. Why would that be 0? Why would, if you integrate it and you have no width, you have height but no width, why is that 0? Because you have 0 width. So that's like saying in a graph, here's your A, it may go up as high as this, but there's no area under the curve, it's just a line, there's no width. So that's why it's 0. So you can't integrate from something to itself, which is 0. The next one, change in the limits of integration. Your integral from b to a of f of x dx is the opposite of a to b of f of x dx. So if you change your limits, if you swap them, you get negative out of that. And there's times we do that, it just makes things more convenient. If you're integrating a sum, this is a sum, that's the sum of the integrations. So you can integrate them separately, and that's just their sum. Same thing, if you integrate a difference of two functions, that's going to be the difference of the integrals. Now here's a big one. If you have some constant times your function, you can pull the constant out. From your perspective, you can pull the constant out, factor it out, and then integrate it. And we're going to see that happen a lot here. Okay. Next one. Last one, you can split up an integral. If you have some value c between 2 points, like you're going like 0 to 10, you could break it up to 0 to 3 and then 3 to 10. So if it helps it for some reason to break it up, and we're going to see why you want to do that. For example, parts below the x-axis, parts above the x-axis. So you want to split it up at that point where it crosses. So you can then figure out the net area. So you can split it up. Integral from a to b of f of x dx is integral from a to c of f of x dx plus b to c of f of x dx. Okay, so how do we use this then? This part is not nearly as bad as I feared it would be. I'm like, oh, I don't want to do all these infinite sums. We don't. They said use the properties of the definite integral to express the definite integral of f of x over the interval from -2 to 1 as a sum of 3 definite integrals. So what we're talking about here is if you were to have integral from -2 to 1 of -3x squared x cubed plus 2x plus 2 dx. By the way, I put them in parentheses. The book doesn't always do that. I do it because I think it's right. I understand the argument if you don't want to do that, but I put them in the stuff in parentheses. So if we split this up into 3 integrals, we have the integral from -2 to 1 of -3x cubed dx plus the integral from -2 to 1 of 2x dx plus the integral of 2 dx from -2 to 1. And what they're saying we can do is that part we can move the c out, was for number 5. We can pull the coefficients out. So it'd be -3 integral from -2 to 1 of just x cubed dx plus a 2 integral from -2 to 1 of x dx plus integral from -2 to 1 of 2 dx. They're leaving the 2 in there. You could pull it out, put a 1 in there, but I don't know what's the difference. And that's it. That's all they're asking for this. Same thing for the next one with the intervals 1 to 3. So we start with integral from 1 to 3 of 6x cubed minus 4x squared plus 2x minus 3. So does someone want to tell me what the, give me the first integral?
Integral is 1, 3, 6x.
Good, dx. Someone give me the next one.
Yeah.
We're doing this term now. Bless you. 4x squared dx. Plus, what's the next one?
3, 2x squared.
Just
2x.
2x dx. And then
3, 1 to 3. Oh, yeah, negative 1 to 3, 3 dx.
good. Now the next step is just to factor out coefficients. So what's that going to look like?
6 integral 1 to 3 of x to the third dx.
Okay.
Minus 4 integral 1 to 3 x squared.
Good. Yeah.
Plus 2 integral 1 to 3 x dx.
Good.
Um,
Yeah. That's it. That's all they're asking for. Yes, I do.
So why do you make that one the way it is? Why don't you pull up?
You can pull it out and put it to one there instead. It really doesn't matter
Right.
if you. So yeah, you can't leave nothing in there. You could put a 1 in there. But I guess the prevailing thought is a 1 or 3. I mean, it's going to be, it's a constant there regardless.
I have a question about the problem before that.
Yes.
So why did the integral, the bottom part, change from -1 to
Oh, because I got confused. That was just a dumb me thing, not a. Thank you for asking that, though. That's just a stupid mistake. It shouldn't have at all. That was just like dyslexic me, okay? I say that not making fun of dyslexic people, just I made a dumb mistake. Okay, let's try, what do we want to do here? Okay, this is a fun one. If we know that integral from 0 to 8 of f of x dx is 10 and 0 to 5 of f of x dx is 5, find it's going to be the integral from 5 to 8 of f of x dx. So we know it is the whole thing. We know what part of it is. What do you think the missing part is? So what they're saying in that step 6 or the property 6 is that the integral from 0 to 8 of f of x dx is equal to the integral from 0 to 5 of f of x dx plus the integral from 5 to 8 of f of x dx. So it splits it up. So what numbers do we know? So this is 10 here. And the next part is 5. Plus, we don't know this, integral from 5 to 8 of f of x dx. Is there a way to find that last part?
Yeah, it's got
Just subtract, yes. So 5 equals the integral from 5 to 8 of f of x dx. That was tough, yeah. That'll keep you up at night. Okay. See, you got at least one thing to talk about here. This is the same type of process. I'm not going to go through that one. And the last thing here is the comparison theorem. If f of x is greater than or equal to 0 and a is between x is between a and b, then we have f of x dx is greater than or equal to 0. And if f of x is greater than or equal to g of x, then their integrals will be greater. Then the f will be greater than g. And If m and n are constants such that m is less than f of x less than m for the interval, then our m, lowercase m, times the interval, it's like basically saying this. Here's your curve. Bless you, yes. Here's m, the lowercase m, here's uppercase m. The area under the curve is going to be between the lowercase thing and the uppercase thing. So I feel like it's makes sense to me. I just don't want to throw anyone off. I mean, what I'm saying here with it is, if you have this is your lowercase m, and then you have another one that looks like this is your f. There's that area compared to this area here, which is your uppercase. My uppercase is not looking uppercase. There. So that's what I'm trying to get at there. If you have it bounded, then you're going to end up with a rectangle below and a rectangle above your actual thing. Okay, comparing two functions. So f of x equals the square root of 1 plus x squared, and g of x equals the square root of 1 plus x over the interval. Compare them. Now, in the case, I really wanted to do this on Desmos, but I'm just going to draw it up here. Your square root of 1 plus x squared has a graph that looks like this. It's not quite a parabola. Your other graph, the square root of 1 plus x, is a square root of x function shifted to the left by 1. So it's going to give you coming up like this. And so you have an interval where your f of x is below the g of x. And they're just after us to find what's happening with that. And that's going to occur from 0 to 1. So what they're saying is that the integral from 0 to 1 of g of x dx is greater than the integral from 0 to 1 of f of x dx, because g of x is above f of x in that area. So it makes sense that the area under the curve for g of x is more than the area under the curve for f of x. And that's it for that part. Okay. So, yeah, where would it be bigger? And it's going to be bigger. And when you graph it out, you can see, and if you're doing Desmos, you can click on that intersection point and it'll give it to you.